So our next section, 4.2, we're going to talk about the applications of the second derivative. So here I have some graphs that I put on your in your notes, and I want you to consider the following graphs of population growth from 1950 to 2000. So this graph is world population, and then on the right here I have US population. So as we can see, both these graphs are increasing. Right? As I move from left to right, it's going up. But you can see the population of the world is increasing at a much quicker rate, right? It's going up, it keeps going up. Now, US is increasing, but it's really kind of leveling off. So it doesn't look like such a well-defined growth rate. So we can see the world population, the pace of the population growth way outweighs what the US is. It's actually decreasing the pace for US and it's increasing the pace for the world population. So down here, I just have again the same graphs as up above, and then the tangent lines are drawn. So you can see that the tangent lines for the world, they're getting steeper as you move from left to right. Whereas the tangent lines for the US, you can see that they're getting less steep. They're flattening out as you go. So that tells us that in the US, we're not having a huge population growth as it is in the world in general. So we're talking about concavity. And when we talk about concavity, we talk about concave up or concave down. When you have concave up, think of a cup. So a concave up function, if it was like cup-like, it would hold water. And then concave down is just that cup flipped over. So we have concave up, and it's decreasing. And then concave up, and it's increasing. So concavity has nothing to do with whether it's increasing or decreasing. It really is telling us how the graph is shaped. And then again, concave down, decreasing, concave down, increasing, which is what the US population growth we were just looking at. So the steps to find concavity, and I'm going to do these problems out for you. First, we have to determine the value where the second derivative is 0 or undefined. Right? That's exactly what we did when we were finding critical values for the first derivative. But the first derivative tells me where the function's increasing and decreasing, and the second derivative tells me the concavity of it. So we first have to find where that second derivative is 0 undefined, put those in the number line, just like we did before. Pick test values. Where the sign is positive, then the graph is concave up, and where it's negative, the graph is concave down. Alright, so the first example that I had, we have y equals x cubed minus 6x squared plus 4x plus 4, and I want to determine concavity. Alright, so I need the second derivative. So the first derivative, I get 3x squared minus 12x plus 4. And the second derivative gives me 6x minus 12. So that is where I need to know where is it 0 undefined. So it's not undefined anywhere. But I can find out when it's 0. So 6x minus 12 equals 0, which means 6x is 12. So x is equal to 2. So I have to check around 2. So I need to pick something to the left of 2 and to the right of 2. So I'm going to pick 0, just because it's always an easy thing to pick. And then 3. So here's my second derivative, and that's what I'm plugging in 0 and 3 to. So when I plug in 0 into this, I get a negative value. And when I plug in 3 into this, 18 minus 12, I get a positive value. So if it's a negative value, it's concave down. If it's a positive value, it's concave up. So I am down on the interval from negative infinity to 2, and I'm concave up on the interval from 2 to infinity. Alright, so our next thing that we're looking at are inflection points, which goes along with concavity. So I'm going to go back to the handout that I have typed up for you. And we have this function here, f of x is x cubed. So you see my function is increasing and it continues to increase, right? So it increases everywhere, but it does change concavity. Up until it hits 0, this is concave down, and then after it hits 0, it becomes concave up. So we have a name for that, and it's called an inflection point. So an inflection point is where I change concavity from down to up or up to down. That is my point of inflection. So we're going to do the same thing. We have f of x is x cubed. And first I looked at the first derivative. So f prime of x was 3x squared. It had a critical number of 0. So when you plug in stuff to the left or right of 0, you get positive. So that told me that it was increasing everywhere. Again, this is the first derivative. So positive means increasing for the first derivative. Then the second derivative is 6x. 0 is what makes this derivative 0. So again, I put that on. And now the second derivative tells me about concavity. If I pick something to the left, -1, and plug it into this, I get a negative. And to the right, I get a positive. So it's concave down, and then after 0, it's concave up. Because this actually existed 0, that's where my point of inflection is. And you can see again, it was concave down up until it hit 0, and then it switched concavity and it became concave up. Alright, so we have y equals x squared over x minus 1. And we want to determine concavity. So before I do anything else, I want to say that x cannot equal 1 because I'm not allowed to have division by 0, which is going to be important when we go to determine, because I can't have a point of inflection at some place that the function doesn't even exist. So I'm just going to write out the first and second derivative. And you can do those out yourself later if you want to practice that. So here's my second derivative. The only thing that makes it undefined is 1. So I still have to look on either side of 1, but I know that I am not going to have a point of inflection there because the derivative doesn't exist. But I'm still going to look around 1. So I'm going to pick something to the left and then something to the right. So if I pick 0 into this, I get 2 over -1 cubed, which is a negative value. So that tells me it's concave down. And if I pick 2, I get positive. And that tells me it's concave up. Let's talk about the first derivative for a little bit. We know 1 can't be in there, so 1 would be on our number line. And if you factor the top, you get 0. You can factor out x, and then you get x times x minus 2, so you get 0 and 2. And the reason I bring that up is because I'm going to show you the graph, even though we're talking about concavity. But if I look at the graph here, that 0 and 2 were critical numbers, and that actually is where I have my local max and mins at. So the function was increasing and then decreasing. This 1 it's not there, but there's a vertical asymptote at 1, and that's where I had to jump over because it wasn't in my domain. So what we found is it's concave down up until we get to 1, so negative infinity to 1, and we can see it's concave down, and then from 1 to infinity it's concave up. And then the last piece of this section is the second derivative test. So what's really cool is we can use the second derivative to determine whether we have relative max or mins. So here I just have the graph of x squared, and it's facing up, and we have a relative min here. This is a graph of negative x squared, so it's just facing down, and we have a relative maximum here. So the second derivative test tells me, because of this concavity, right, I'm concave up here, I'm concave down there, if I compute the first and second derivative, find all critical numbers from the first derivative, and then take those critical numbers, plug them into the second derivative, it's going to tell me whether it's a max or min. So if f double prime of c is less than 0, which means it's concave down, I had a maximum. If f double prime of c is greater than 0, which means it's concave up, I have a minimum. If it just equals 0, the test fails, and I have to go back and use the number line. But a lot of times this will work, and I don't have to go back and do that. So I'm going to do this last example. We have f of x is equal to 1/3 x cubed plus x squared minus 15x plus 7. So my first derivative is x squared plus 2x minus 15, and my second derivative is 2x plus 2. Alright, so I'm going to work with the first derivative. Set that equal to 0. And I get two solutions, -5 and 3. Now I'm going to take these critical numbers and plug them into the second derivative. So I want to do f prime of -5, f double prime of -5, and f double prime of 3. So when I plug in -5 into the second derivative, I get -10 plus 2 is a -8. When I plug in 3, I get 3 times 2 is 6 plus 2, which is a +8. So it was concave down at -5 and concave up. So therefore it tells me at -5 I have a relative max. And at 3 I have a relative min. So I use that second derivative test, and I don't have to use the number line for the first.